a versatile robotic end actuator. We present here a design for a robotic end actuator which is dexterous, strong and accurate, hardy and impact resistant, human scale, inexpensive and easy to mass produce, simple to set up and control. I will now illustrate each of these points using a demonstration article that we have constructed. This design allows for many different configurations with different number of fingers, joints, and degrees of freedom. For the purpose of this demonstration, we have made an actuator that corresponds to a human right hand, but with no pinky. The hand consists of 3 forward-facing fingers, the middle, ring, and index fingers, and a backward-facing thumb. Each finger has 3 joints. Each joint can be articulated independently. Each joint can be flexed up to 90 degrees. The thumb is opposable, allowing it to touch the tips of each of the other fingers. The ring and the index finger can be spread out by up to 15 degrees and inwards by up to 5 degrees from the center line. The thumb can rotate around 20 degrees from its center position. This allows it to reach the tips of the other fingers. The fingers are attached to a palm, which in turn is attached to a double-jointed wrist. The wrist allows the entire hand to be articulated up-down and side to side by up to 30 degrees from the center line. As you can see, the demonstration article achieves a dexterity that rivals that of a human hand. All motion are driven by cables. Cables run from the articulated joint through a system of pulleys within the fingers, through the moving joints, through the palm, and through the double joint into the arm, which contains the motive driver. Within the palm section, specially placed pulleys arrange the cables so that they exit the palm in a regular 6x6 grid. This allows all the cables to traverse through the wrist double joint, which is a pinch point and otherwise hard to traverse. In the demonstration article, the cables are coupled to geared DC motors which pull on the cables. For the purpose of this demonstration, we have constructed a simple stack of motors and belt tensioners. There are, however, a multitude of options for powering the cables, including pneumatic muscles, piezoelectric actuators, and other types of motor gear arrangements. For each cable, we use a DC motor and an attached worm gear. The worm gear acts to multiply the torque as all motion operate under a significant mechanical disadvantage. In the demonstration article, we use 2 mm diameter UHM WPE cables, which have a maximum tension of 500 pounds. With an approximate 10-to-1 mechanical disadvantage, each joint can potentially apply a force of 50 pounds at the end of its segment. The limiting factor is the material used to build the surrounding load-bearing parts. The demonstration article is built on a Foam Labs engineering photopolymer resin. As you can see, the motion is smooth and precise, while the cables are under a large amount of tension. The cables are always supported on the U-grooves of pulleys within the fingers and palm. Inside the pinch point of the double joint, they are supported on rollers. The cables are always on moving surfaces. As a result, they can slide smoothly while under a very large strain. If the plastic parts are replaced with steel or aluminum, we can easily make this design apply higher forces in the order of hundreds of pounds of force on each finger joint. Next, I will demonstrate the precision of the motion. I will energize the DC motors driving the finger joint for just 10 milliseconds and will repeat this action 10 times. The motion is precise and has a sub-millimeter spatial resolution. In this design, we have used inexpensive geared DC motors to achieve a dexterity, strength, and precision that rivals that of a human hand. We have designed the parts of the hand with tight tolerances in the order of 0.3 millimeters. Furthermore, we have added spacers to ensure that the cable pathways have no nooks or crannies larger than 0.5 millimeter. This is much less than the cable diameter of 2 millimeters. If the hand experiences sudden impact, the belt tensioners will yield to help absorb the shock. Subsequently, as the tensioners retighten the cables, any displaced cables will simply slide back into their pulley U-grooves and their normal paths. It is impossible for the cables to fall out of their normal path since they have nowhere to go. The design is extremely robust against vibration and impact. The prototype is approximately 4 times human scale to ease construction. However, this design can be easily scaled down or up depending on needs. A human scale hand is strong and dexterous enough to manipulate human tools. The bill of materials is less than $250. Each hand can be assembled by unskilled workers in about 6 hours using simple tools. We choose the design of the hand around easily available hardware that can be easily sourced from multiple vendors. We choose to reuse the same parts, bearings, rollers as much as possible so that we may gain bulk ordering discounts where possible. We estimate that the total cost of manufacturing is less than $500 per hand. In this section, I will illustrate how we achieve position detection of the actuator. The actuator does not have any flex sensors, servo motors that offer position information, or any other mechanism for detecting the position of the fingers. The end actuator has QR codes placed at each joint as shown. Each QR code will have a numerical value that is unique to the finger joint. We will use inexpensive cameras placed on the host robot's workbench to pick up the position of the QR codes. QR code detection on video feed can be done accurately and rapidly by using existing cloud services. Once the QR code detector picks up all the locations and 4 corners of each QR code, we can solve for the position of the fingers. During motion, the solver is constrained by the dimensions of the hand and prior configuration. Therefore, even if most of the QR codes are obscured by objects in the workspace, we can still obtain a very accurate position of the hand. A position accuracy of 1 millimeter is possible using high-definition webcams placed around 2 feet from the actuator. We believe a low-cost, strong, and dexterous hand offers many real-world applications, which I will illustrate now with examples. A one-hand configuration can be a useful accessory for wheelchairs, automobiles, or other mobility aids. For example, loading groceries or plugging in an electric charger for the elderly or disabled. The user can directly manipulate the arm in this case. The low cost of these arms opens up vast possibilities of using it in relatively low-value applications like casual home automation, such as chopping up produce or washing dishes. Here, a machine learning software layer will be needed. The forearm configuration is especially interesting since it allows the robot to walk over to where it is needed. The legs in this case are fully dexterous, allowing the robot to grab aids in the environment when moving. Such a robot can climb trees and buildings if needed to get to hard-to-reach places. Since the hands are robust and tough, each robot can easily carry weight and absorb impact while wading around in wet, hot, or otherwise hazardous environments. This may afford applications in search and rescue, bomb disposal, and other hazardous activities. This concludes the presentation of our versatile robotic end actuator.